Should have perhaps checked.
Hi, Will.
Hiya.
Welcome to Talk of the Day, the Build-a-Baddie workshop. I'll hand over to you.
Brilliant. Okay, yeah, thanks very much. Hope everyone can hear me all right. Welcome to the Build-a-Baddie workshop. So the plan here is really to have a little bit of fun. A lot of the stuff we're going to go over in this isn't going to be in like excruciating detail, but it's kind of just a glancing blow, and hopefully it'll be enough to get you into the idea of AI in games and such. So that's the main idea. There's a couple of things I'm going to go over quickly before we start. First of which being, yes, there's a sink in the background. It's not going to be going anywhere, don't worry. And the second part of that is I'm not streaming from my bathroom, just to be clear. I'd had Chris bring that up, so I thought I'd just kind of clear that up with you as well. And of course, the last thing is, if you've got any questions at any point during the presentation, just feel free to put them in the chat. I think as long as you're happy with it, I think Chris is going to put them up on screen just so that everyone can see and hopefully get involved with answering the question. So, right, let's get started. A little bit about me, first of all. I don't think my animations are working, but that's fine. So I'm a third-year games computing student at the University of Lincoln right now. I'm currently really into, obviously, the idea of like AI in games, as you'd hope from someone delivering this presentation, and more specifically, I guess, as an umbrella to that, like emergent storytelling in games, like how we can basically make code to tell a story, or more specifically, help the players who are playing the game tell a story, make a story, and AI can be a really big factor to that. Those are two kind of things we're going to be really touching on with this presentation, and there's two things that I'm really, really into, and I hope that you'll be as well by the end of this workshop. Last year I took a placement at a company called Rare, who are a UK-based games development studio. They go back about 30 years or something, long time. They've made a lot of kind of games that you probably know of, Banjo-Kazooie, GoldenEye 007, Perfect Dark, Viva Pinata. There's a lot. There's many games. But I was fortunate enough in the time that I was there to work on Sea of Thieves, and more specifically like the AI systems, as well as some other kind of loose bits around the code base for Sea of Thieves. But that was a lot of fun. So I'm not going to be touching too much on that today, but I'll use it in a couple of examples. I just thought I'd give that as a bit of background. And of course, if you've got any questions pertaining to like industry work and how to get placements and things, I'm happy to touch on that, but that can be kind of, for another time perhaps. But here we go. So what do I find exciting about AI in games, and like what do I hope that you will also find exciting about it? We're going to cover in this workshop. Well, I think AI for games kind of has a stigma of just being this basic system of that defines like minute-to-minute interactions for like an NPC, right? I think when you think about AI for games in general, you think of the Grand Theft Auto pedestrians walking around the street. Yeah, sure, that's AI in games to some degree, but we kind of want to look at AI as more of like an umbrella to lots and lots of different systems, like it really is. So I think AI is super fascinating to work on in games because it helps make games feel responsive. Actions that kind of you do as a player reflect on AI and things in the game world, and kind of really make you feel like the game's responding to the stuff you're doing. And it makes things replayable as well, particularly if you've got quite an open and emergent AI system. Stuff like that can be really, really replayable. You can come back whenever you want, and it'll be completely different, but it'll always react in like a logical manner, I suppose, to the way that you're kind of treating it, I guess, if you want to think of it that way. But another kind of fascinating thing about AI in games is just how far it's sort of come in terms of like, I've watched Queen's Gambit on Netflix recently, and it's kind of brought me on this little like a rabbit hole of automated chess and things. Obviously that's not what the show's about, but it's chess basically, and it just got me thinking about chess and how the old kind of Deep Blue AI robot that they called it would predict chess moves and essentially be a very, very primitive form of like game AI. To where we are now with things like Alien Isolation, Watch Dogs and things that we'll pick up on later. But it's basically it's a really really fascinating field, and it's only getting smarter. Is the point I'm trying to make. The very definition of kind of artificiality in artificial intelligence is kind of just blending more into just real intelligence to some degree. But yeah, there's so much to cover anyway, and I'm not going to cover it all today. This is just going to be like a glancing 101, get you excited and then leave sort of thing. So here we go. So I don't completely agree with this quote in a literal sense. Maybe I think it's a little bit extreme, but a year spent in artificial intelligence is enough to make one believe in God. And I think while that might be a bit extreme for some, I think we can interpret this in quite an interesting way, that it is quite threateningly apparent when you start working in AI how simple it really is to actually make something seem intelligent. And there's kind of many ways that you can do that. And AI isn't really this black box of trying to mimic the way human brains work and things. It's not that at all. It's just trying to mimic this idea of intelligence, which kind of brings me on to this idea in AI of smoke and mirrors, where we're really just trying to sell the idea of something rather than trying to completely simulate it itself. And if you're not familiar with the term smoke and mirrors, it's something that kind of gets used a lot in AI, the term at least. And it's just this idea of selling something that isn't really there. And it actually comes from, if you're curious about the picture, this machine here, which is called Pepper's Ghost, which is like is a very primitive kind of form of making ghosts appear, I suppose, for entertainment purposes, I guess. And you sort of guess where that's going. It used smoke and mirrors to make ghosts and things appear. But the point of that analogy is that we use a lot of stuff that isn't really there to mimic and sell the idea of actual intelligence. And particularly in games, that's quite important, just because of we've got time constraints in frame time. We've got to make it fast. So yeah, so we'll get started. So first of all, we're going to cover decision making. So behavior trees, predictive and proactive and reactive ways you can do decision making for AI in games. And then we're going to touch on Radiant AI. I've realized this is an older version of the presentation, so I apologize for that. There might be a few spelling mistakes and some of the animations might not be there. I've realized that now because Radiant shouldn't be there. I renamed that, but we'll move on. So decision making. I mentioned there's two kind of main ways of doing decision making in games. There's probably more, but just if we're looking at it from quite a reductive kind of point of view, we've got proactive decision making and reactive decision making. Proactive is more looking ahead, like a goal-oriented solution. A hint on what we're going to be talking about in a minute. And reactive, which is more of a I'm in this situation now, so I will do this next and this next, followed by this. We don't really look for an end goal. We kind of just go for go on the fly decision making, basically. Behavior trees or decision trees. This is a form of reactive decision making, and this is probably the most well-known way of doing like AI in games, just because it's old, it's tried and tested, and it just works very well, and it's very simple to understand as well. So if you think of it as an upside down tree, that's the way we sort of traverse it. We traverse from the root down to its branches and leaves or nodes, from left to right. So we go up, back, down, and from the top left to right, basically. So there's a little kind of demonstration down here of how it would work for a simple kind of walking into a door, opening it and closing it again, how that sort of cycle would look if you were to wrap it up in a behavior tree. So we have our sequence here where we walk to the door, we go back up, we open the door, and then we walk through the door, and then we close the door. Simple as that. Very simple. But I want to draw your attention to this here, this sequence. This sort of thing here is what we'd call a composite node. And composite nodes are what basically dictate the flow of the behavior tree. And there are two main types of those. So we'll go on to that now. So the two types of composite nodes you can get are sequence nodes and selector nodes. So the sequence is the one we just saw a minute ago, and the idea of a sequence is it aims to execute all of its leaf nodes, or the children nodes underneath it, until one of them fails. And then as soon as one of them fails, we go back up to the top again, and that's sort of considered then that the composite node has failed. The sequence is broken, the sequence failed, however you want to put it. So if you think of a sequence node as it runs until failure. The opposite to that is a selector node, which, if you want to look at it the other way, is it runs until success. So it will go through all of the children underneath it, and will return a pass if any one of those nodes passes, right? So the selector, it doesn't really matter if it fails. It will just kind of move on to the next step, if you get what I mean. So we'll work through these examples. I hope that will be a little bit clearer. So if we look at this, so this is exactly the same demo I showed a minute ago, with this like walking to a door, opening it, and closing it. If we look at this and consider a failure at one of these points, so we go to our sequence, we walk to the door, that passes, we go back up, then we go to open the door, and say our open door fails, say the door's locked or something, this sequence is now broken, so it will go up, this sequence counts as a failure, and then we go to whatever is next on the behavior tree. When we look at this tree here, this is exactly the same tree, I should point out, minus the open door here has been swapped over to a selector. And this is kind of where this idea of failure handling and things come in with behavior trees, which I'll touch on that in a little while. But if we run through this again, but with a selector, so we go through our sequence, we walk to the door, we go back up, we go into our selector now, and if you remember, a selector will run until a pass rather than a failure. We go and try and open the door. If this open door passes, great, we'll break the sequence, we'll return a pass, and we'll go straight up and carry on. So that just carries on as if it was this behavior tree, right? We passed open door, we walk through it, and we close it again. Let's say we tried to open the door and it failed. Well, it failed, which is fine because it's a selector. It will keep going. It will only return when we get a pass. We go back up to the selector now, and we start a sequence here where we try and unlock the door and then open the door. Of course, how a sequence works: if this fails, any one of these fails, we go back up, and that's a fail. So say we walk to the door, we try and open the door, we can't open the door. We go back up here and we try and unlock the door, and we can't unlock the door. Let's say that this sequence fails, so we go back up and we try the last approach, which is to smash the door. Obviously, that's the logical approach that an AI might take in a case of like the mini games would do that. I can't think of an example right now. I'm sure you can, but you can kind of see how these behavior trees can really start to mimic this kind of complex decision-making behavior. And that's why they're used so frequently in industry. So I hope all of that was clear, by the way. If anyone has any questions about that, feel free to pop them in the chat, and I'll try my best to answer them. But if we look at the pros and cons of using behavior trees, the pros and cons are going to be more apparent when we kind of contrast it with other strategies. But yeah, for now, we're going to look at what the advantages and disadvantages of it. So first of all, behavior trees are predictable, which can be a good thing because it's easy to debug. If you have something going wrong in one part of your behavior tree, it's quite easy actually to then find that exact point on the tree, look at the logic and the way it's flowing, and then figure out what's wrong with it. Everything's basically a script if you think of it that way. The AI agent is essentially sat there reading from a script, saying, first I'll do this, then I'll do this, and then I'll do this if this fails. It's really easy to jump in and figure out at what point in that decision-making process something went wrong, if that makes sense. So that's good. That's a really good thing about behavior trees. They're designer authored. So this is something that's really, really big, particularly in like AAA games. Having something designer authored means that a programmer who's set up this system doesn't need to kind of get under the hood again to mix it around and make it all work and build these trees. You can actually build a modular system for a behavior tree that you can pass off to a designer who can then go to town on making it the best behavior tree you've ever seen, which is really, really, really good. This is something particularly great in industry because designers obviously want control over everything that our AI do. And they don't really want programmers to be doing that. Trust me, they don't like that. um, yeah, they're readable as well. There's a reason that decision trees, binary trees, flowcharts are so kind of big in areas just outside of computer science as well, in maths and science, and even outside of that, business and things use flowcharts and things everywhere. And there's a reason for that, because they're just really readable. They somewhat mimic the way that we go about our decision making process. We kind of go from one state to another, and it follows like a logical process. So it's really, really readable. And you can kind of see that when we look at our previous example, just kind of how readable that is, and just how easy it is to understand what an AI is thinking, which is fantastic. So it can handle task failure. I touched on this a minute ago when we were looking at the selector nodes. If a task fails, that doesn't necessarily matter, because you have another case where you can say, okay, well, if this selector fails, we'll branch it off and just try something else. Like if we tried to unlock the door, that didn't work, we'll smash the door instead. So you can actually make kind of good of a failure and make some really, really interesting gameplay mechanics out of that, which is something we're always looking for, really. Just trying to make something seem believable. And obviously dealing with failure and things for our AI is really important to making, selling that they are actually, somewhat sentient, that they're not just going to be like, oh, looks like this door's locked, away we go, I've lost interest in finding this player now. But there we go, that's some really great things about behavior trees, and that's a reason why they're so popular. Although there are a few things that behavior trees can't do, or don't do so well. So the solutions aren't unique. Obviously, a designer has to sit there and go through and make these behavior trees. So to an extent, yeah, they are artificially intelligent in the sense that they're kind of making decisions somewhat on their own. But the solutions to coming up, the solutions to dealing with these problems, they're not unique. Every single AI on the map presented with this problem is going to solve it exactly the same way, which can be a really good thing for consistency. But if you're looking at trying to make, emergent gameplay and things, and something, engaging and replayable, that's not going to work so well. So that's potentially a problem with behavior trees. There's no pre-planning or proactive decisions. So this comes back to that idea I mentioned with reactive and proactive decision making. A behavior tree is what we'd consider a reactive decision maker. We go from one node to another, and we don't really pay attention to the end goal. We kind of just look at the node we're at now and then go down it, just like a flowchart would. And that's because under the hood, a behavior tree is really just a finite state machine. So that could be a problem, that the AI doesn't seem to take in much context to its surroundings, potentially, with a behavior tree, just because it's looking at the here and now, and it's only really paying attention to what it has to do next, what it just did, right? So we'll touch on why that's a bit of a problem in a minute when we look at the proactive side of decision making with a slightly different technique, but that's worth bearing in mind that they are not proactive decision makers. So they're state-based. I mentioned that a minute ago. Being state-based is okay. Obviously, with a finite state machine, there's a reason they exist and why they're used, but they don't really model quite how like a human brain would work, right? If we're presented a problem, our brain doesn't work in states necessarily. If you want to, open a jar that's on a high shelf, we have to climb the shelf or whatever, grab the jar, get down carefully, undo the jar, whatever. We don't think of that in terms of stages necessarily. We think of that as steps, right? I don't know if that analogy made sense. I think it made sense in my head. But essentially what I'm saying is we like to use like a methodical step-based process, right? Where we have an end goal in sight. We don't tend to think in states like a finite state machine. That's just not how people work mostly. There's perhaps some exceptions, but we're not talking about that today. So yeah, again, there's a con. I mentioned that predictability was perhaps a good thing. When you think of it on the flip side, it's predictability is also, it can be pretty bad. People can, get AI stuck if they know a certain way to mess with their behaviors. I know in Sea of Thieves, people did that a lot. They kind of picked up that skeletons and things would do the same thing over and over again, exactly the same way, and it was very, very easy for someone to kind of come in and basically put their foot in the way. figuratively speaking, and mess the whole thing up. So predictability is also quite boring sometimes. If you know what an AI is going to do every single time, step by step, it just becomes less engaging. It doesn't feel like a genuine thinking entity that you've got to try and outsmart, right? So predictability can be a bad thing, although it is quite good on the development side. Probably not quite so good for players. So I mentioned Sea of Thieves a minute ago. I said I wasn't going to mention it much, but yeah, all of the AI, every single AI entity in Sea of Thieves was made using behavior trees, which might stand out as a bit of an unusual choice considering kind of how open the game is and how it's kind of based on this tools and not rules system. It's unusual perhaps that behavior tree is chosen, but again, it's AAA, and from the guest development side of it, behavior trees are much easier to do and much more predictable, obviously. So we've got a question. Oh, is this a question? Thomas, predictability. Oh, I don't know if we want to put this on screen or not. But yeah, so Thomas said predictability gives familiarity to the enemies, so the player can play. So the player can play and each time get more comfortable with the enemy and devise tactics on how to combat it, like in Cuphead and Dark Souls. That's exactly right. So that's something I didn't mention actually in the previous slide. But yeah, Thomas is quite right. A really great thing about behavior trees is that oh, thank you, Chris. Is that yes, they're predictable, so players can work on skill, you know, to build up a skill to fight a specific boss. I mean, that's kind of intrinsic to the idea of like boss fights and things in Dark Souls, as Thomas mentioned, where you kind of need to get used to the nuances and specific behaviors and signs that come from a specific boss in there to beat it. So it's definitely a point worth making. So yeah, the next thing I'm going to talk about is the other approach you can take, which is goal-oriented action planning, or GOAP. And this is more of a proactive look at AI planning. So I apologize, there's a lot of text here. Oh, excuse me. I apologize, there's a lot of text here. So I'm going to try and sum this up as best as I can. But everything in red, essentially, is something that's sort of a keyword that I'm going to be mentioning a lot. So the idea of goal-oriented action planning, or GOAP, I'm going to get sick of saying goal-oriented action planning. Rather than using predefined strategies like we see with behavior trees, GOAP actually provides AI with a goal instead and a set of actions. And then the AI itself can look at those actions that it has access to and try and figure out the best way to get to its goal. So rather than drawing kind of set lines between every single possible action to get to the specific goal we want, we just give it a goal, give it a ton of actions, and then it kind of goes and figures out the most efficient way to do it itself. Chris said, yes, people can be predictable too. Yes, quite right. If you're trying to simulate that, obviously that's really handy. And obviously, I don't want to be putting both of these ideas down this behavior tree system and goal-oriented action planning as two kind of, you know, rivaling things. One's better than the other. That's absolutely not the case, because there are instances where both of them are usable. And sometimes, yes, predictability can look intelligent. I think to an extent, I think people do move in predictable ways. When you look at perhaps like first-person shooters and things, you know, soldiers are trained in a specific way to follow, you know, predictable actions, I suppose. Not intentionally predictable, but there are set kind of things they've been trained and taught that would make it seem predictable, the actions they take and how they, you know, react to certain scenarios. But back to action planning. So there's a couple of keywords here. These are basically the three main keywords we're going to be touching on and we're going to be needing for this system to work. So we have this idea of a world state, and a world state is a set of facts about the environment. If I were to give a fact about the environment, my environment, I would say the weather is sunny outside. I had to really think about that then. The weather's sunny outside, or the door is closed. Things like that are just facts about the game world, which the AI can then use to influence its planning. And that can also help define a goal. So a goal is a set of these world states that have to be true in order for that goal to be considered a success, right? So, say the world state is that a world state fact would be that the door is closed, right? You could set a goal for that AI that door is not closed. So it'll try and find a ton of actions then that build up and result in the world state of door closed being door open, right? So yeah, an action is an AI so an action is something that an AI agent can complete in the game world, which will influence the game state. So opening a door will be an action, right, that influences the game state, the world state, sorry, and now makes door closed, door open. There's a lot there, I know, but you got through that one. So we're going to do more of an example in a minute. But essentially, just to kind of summarize what goal-oriented action planning effectively does, if you really look at it kind of abstractly, we take our finite state machine here, or a behavior tree, and we get rid of all the links. We just get rid of them. And then we let the AI actually come up with the links itself and draw kind of a route that it wants to take, you know, the most efficient route potentially. Which you can start to see now why that would be quite powerful in making something like emergent and interesting, because there doesn't have to be a set amount of actions that an AI has, right? You can always add more actions to it. You know, a higher level enemy might have access to more actions, so it can start to make these more complex and more efficient ways to get to a goal. But we'll show some examples in a minute. But I hope you can kind of start to see where this is quite powerful and where you could potentially use this sort of thing. So we're going to introduce two more things here. We're going to introduce preconditions and costs. These are two parts that are kind of, you know, intrinsic to goal-oriented action planning, and they're really, really simple. I really, really hope I don't butcher the explanation of these because they're really simple concepts, but I feel like they can be quite easily over-explained. So I'm going to try my best not to do that. So preconditions, well, actions that we've said, so opening a door or, you know, drawing a weapon, they can have a set number of prerequisites. So say a prerequisite for opening the door might be I am near a door, right? That makes sense. Or you know, a prerequisite for drawing a gun for an AI, the AI needs to have a gun in its inventory. So these prerequisites can help shape the decision-making process, where certain actions might not be used because, you know, it has like a completely unreachable prerequisite, or you can actually start to chain actions together to meet the prerequisites. So we'll look at this example here. So say our agent X, this is just going to be our AI agent that's using this action planner, has a goal to make the world state of player defeated true. So I've got a little label down here if you lose kind of track of what do these colors mean. But we have an action here at our disposal called shoot at player action. It has a prerequisite, a requirement of agent X, which is our agent, holding a gun, which makes sense, right? To shoot at the player, we need to be holding a weapon. And this results in the world state changing, and this results in player defeated being true. So now, for this action, our planner needs to look at the next step. So we have this goal, right? And this action fulfills that goal quite well. It sets the desired world state, but it has a requirement, right? It has a requirement of agent X needs to be holding a gun. So now what the planner needs to do is look for more actions that satisfy that requirement of agent X holding gun. So we look at our action here, as I've just explained, and then we have another action here, equip weapon, and the result for equip weapon is agent X holding gun, which is what we want, right, for the shoot player action to work. So what the action planner actually do is chain these together, and it will almost build a recipe that the AI needs to follow, just like a behavior tree, right, to get the goal that it wants. So, oops, I skipped too far ahead then. So you can see this is kind of what the action plan might look like. It'll first of all equip a weapon because that satisfies this goal, and then it shoots the player because it satisfies the end goal. So I hope that was clear. I hope I didn't over-explain that because that's quite easy to do, I think, with this with these two things. But yeah, if there's any questions about that, feel free, pop them in, and I'm happy to go back. But yeah, for now we'll move on to costs. So cost is the other half of this idea of prerequisites and costs. So as well as having a prerequisite for an action, you can also have costs for a certain action. So you can end up with certain actions being more costly than another. So I've got an example here where Agent X wants to shoot at the player again. But Agent X actually has two guns in their inventory. They have one, which is an empty sniper rifle. It's got no bullets in it. He'll need to reload it, or he wants to use that again. Or a fully loaded pistol, right? So the formatting's gone a bit messy here, I apologise. But you can see that if we want to use the equip weapon sniper action, that has a cost of 8. That has a much higher cost than equipping the pistol, just because we've kind of had to bear in mind that, okay, the sniper's empty, so the AI is thinking if it has to draw this one, it has to reload it before it can use it. So it's less likely to do that than just pull out a gun and shoot. So it's about this idea of like weighing up the costs, right? And obviously, this action is a very, very this action plan, sorry, of like drawing a gun and shooting the player. It's a very, very small goal or set of actions, right? You can have many, many, many of these actions all strung together in a really, really complex decision maker. And these costs kind of help filter it and make it dictate the flow a little better to make it match sort of what we'd be thinking, right? Another example that I didn't put down here is you could consider the range that the enemy's in, the range of the players into the enemy, that you can calculate the cost of using a certain weapon based on that range. Maybe if a target's 100 meters away or something, the AI is more likely to pick the less costly sniper rifle, even though they have to reload it, just because it has that range, rather than a pistol, which, yes, might be quicker to equip, but it's probably not going to be too good at going on 100 meters, right? So hopefully that all of that stuff was clear. But you can see where both of these, preconditions and preconditions, and costs can come in to really start to shape your action planning systems. So I hope the idea of goal-oriented action planning was clear throughout that. I've flown through it very fast, so if that did all go in, that's great. There's perhaps more to it than what I've just explained, but as like a little glancing an entree, I suppose, into that, that's I reckon that's a pretty reasonable summary of how GOAP works. So if you got all that, fantastic. That's really good. Now let's look at the pros and cons of it. So obviously GOAP isn't perfect. There are some issues with it, but we're going to look at the pros first. So it's proactive in its decision making, rather than looking at our reactive behavior trees where we're just going from one leaf to the next leaf, or one node to the next node. We're actually looking at our end goal and actually determining our actions in the meantime based on whatever that end goal is. Essentially, our system doesn't care about the steps involved. It's only interested in getting to that goal, which is sort of the opposite of behavior trees, right? Where a behavior tree has no idea about what the end goal is. All it's interested in is going from node to node, kind of skipping through and just completing the node it's on and following that flow. So this is what we consider proactive decision making in goal-oriented action planning, because we're proactively planning and we're looking at an end goal and basing everything off that. So that's good. It mimics a little better with how we would think, and it makes for some, as you can imagine, quite interesting AI. AI that sort of thinks on its own, or has unique solutions where it, when it's presented with a problem, which is really, really cool. So they're flexible and really easy to iterate on. Yeah, absolutely. I used I mentioned earlier that perhaps, if you're making like an MMO or something, or, a game with boss fights, you can make your AI boss, or the higher level AIs, have access to more actions, right? And that immediately allows them to plan a little bit more efficiently. If they have access to more actions or more specific actions, they're going to make more interesting plans, and there's going to be much more variety. And all you really need to do to improve the way that AIs think with this system is just throw more of these actions into the pool that they pick from. So that's a really, really great thing about behavior trees. Action planners, not behavior trees. Excuse me. And yeah, I mentioned it makes for emergent and exciting player narratives. An AI is never really going to do the same thing again. It will be uh, uh, completely unique, I suppose, and context driven. So you're never really going to get exactly the same thing happen like you would with behavior trees, where they're very predictable and they'll do the same thing over and over again. So yes, unpredictability. That is good, I suppose, in a sense that it keeps you engaged, but I put a little asterisk next to that because we're going to be touching on that with the problems with goal-oriented action planners as well. And yeah, of course, they're unique and context-based decision making rather than fixed states. I've covered that already. So yeah, a problem with goal-oriented action planning, there's not much designer control. Well, there's basically no designer control in the flow of an AI's thought process, right? Because it's just the AI thinking for itself. It's not like a behavior tree where you can basically tell an AI to do this, now now you're going to do this, and once you've done that, do this. It's sort of, you just give it an action and it just goes and figures its own way out. And although that might seem very clever and it might be very smart and it'll look very interesting, it might not be the most, I guess, engaging solution. It might look a little less than real, which designers sometimes have a problem with. Designers want to shape their own narrative, and they don't necessarily want the AI to be doing that for them. I hope that made sense. But that comes down to unpredictability as well. You don't know how it's going to play out until you sort of give it a goal. It makes it very hard to debug, obviously, unless you have like a good sort of framework in place for testing out each of these actions and making sure they're all working, and some debugging in there. But it's going to be very hard to replicate if something went wrong, because you might never get that action again. If you've got a really, really complex set of actions, some specific thing happened maybe that broke the AI, it's going to be really, really hard to then go in and debug that and replicate it. Or reproduce it, as they call it in like QA and things, where they want to figure out what went wrong, and to do that you try and get it to do it again, right? And it's going to be hard to do when you've got such a unique kind of context-driven system like this. So yeah, difficult to debug. It's easy to make it too smart, and I know it seems ironic, right? That we're looking to make something artificially intelligent, but actually, to an extent, we do want to make it artificially stupid as well. And you want to make things fair and balanced. And if we go back to the Dark Souls example, if you imagine Dark Souls using this kind of system, an action planner, it's making a hard game even harder. You can't predict it, and it's gonna every single time go for the most categorically and objectively efficient solution, which isn't necessarily what we want every time, because the most efficient solution certainly isn't going to be the prettiest solution every time, and it's probably not going to be very fair either, let's be honest. So yeah, making artificial stupidity is quite hard, actually. Yeah, I mentioned right at the start, it's surprisingly easy to make something seem intelligent, but there are far more instances of genuinely complex and amazing natural stupidity than there are of like actually really, really smart and complex AI. But yeah, that being said, goal-oriented action planning is a very, very powerful system. Perhaps a little too powerful for games, for at least bad guys in games maybe. But there have been a lot of games that used it. I'll bring this up quickly. Zumba Pup mentioned, for anyone interested, there's a whole host of planning-based AI research out there that's a very active area of research in things like logistics. Absolutely. This is huge, and goal-oriented action planning has been around for a very, very long time. And there's a subset of goal-oriented action planning, which I wasn't going to touch on today, and I don't plan to, called HTT, which is a much newer sort of framework and an ideology for it, which I think it stands for a hierarchical task networks, or HTTN or something like that. But yeah, I think, yeah. But anyway, we're not covering that today. But yes, both of these things are really big areas of research, which are definitely worth looking into if any of this interests you. It's very active. HTN, oh brilliant. Okay, I was right apparently. Yes, Brick Regs, it would make an utterly terrifying survival game. You're quite right. Somewhat ironically, I mentioned Alien Isolation a tiny bit earlier. You'd think a game like that would be using goal-oriented action planning, but it doesn't actually. But Alien Isolation uses behavior trees, which I feel like they perhaps missed out on a little bit with where they could have used a really good action planner. But that being said, I think a lot of the actions performed by the alien, for anyone who's played Alien Isolation, you'll get what I mean. They're very cinematic and they're very deliberate actions, and they're designed in that way to make the game fair and to make the game genuinely scary. But yeah, I think there's definitely room in horror games for some really intelligent AI that's really trying to outthink you. So I'm sure there's some out there. But yeah, here's a few games anyway that use it. You'll notice quite a lot of them are quite old, with the exception of Shadow of Mordor, and I'll come back at the end to why it might be the case that they're all a little bit older than you'd think, because this is quite new technology. At least it looks it, right? When you look at it in contrast to behavior trees, you think, wow, this is more like modern day AI. But yeah, we'll come back to that. Yeah, so we got a question from Thomas, if we want to pop that on screen possibly. So is goal-oriented action planning more intense to compute as opposed to behavior trees? Not necessarily. I think again that's probably down to the implementation and how you set it up, but it certainly doesn't have to be. And at least in most modern game engines, or at least most modern iterations of behavior trees, it's all done latently, so it's run over a series of frames. It doesn't have to be all computed in one frame, and in fact, that kind of works in our favor a little bit for the whole believability. Our brains don't fire at 0.016 second update rates. Our brains don't necessarily run at 60 FPS. We're not going to react to something happening straight away. We do have a bit of latency, and if anyone's into biology, I don't know this, but I'm pretty sure they've figured out the actual the latency of our neural reaction times. I think they have that as a stat somewhere, which is quite interesting. But yeah, so you can make this stuff latent, and you can do it over a series of frames, and it can be really fast. But back to the question you asked is GOAP versus behavior trees, which is faster. That's totally down to implementation, I think. I would be more inclined to believe that GOAP is slightly slower, just because there's more kind of decision making and more computing that has to kind of go on to actually come up with a plan, right? Where instead of behavior trees, I'm actually reading from a script, just a set list of actions with set latency basically. And as well, obviously, an action plan could be pretty long. You don't know how many actions are going to be part of that plan, so that actually carrying out that action could be quite slow. But yeah, that's a very good question, and I hope that was a reasonable answer. Yeah, okay, so that's the more complicated bit out of the way. That was decision making. So we've covered behavior trees and goal-oriented action planning. And now the second part of this is emergent simulation. I've changed it here apparently. So apparently here it does say emergent simulation and not radiant. But yeah, so this stuff is really juicy. This is the stuff that really fascinates me, and it's basically about simulating wider worlds, right, outside of what we can just see as the players. So if anyone knows what this game is, it's if you know, you know. I'll be touching on this a little bit in a minute, but anyway, here we go. So just as we'll go back for a minute, I'm getting too far ahead. So emergent simulation is this idea of simulating stuff that we can't see. We're kind of used to in games like GTA, or when we're playing with bots in Call of Duty or something. We're just simulating kind of the AI agents that we can see, and they're all fully simulated at all times, kind of doing their thing. But when you look at kind of a big emergent open world, and just simulating the stuff that's around us, isn't that interesting, right? It'd be great if we had a system where we could simulate an entire world, or like an entire level. But that's quite computationally expensive. So there's lots of tech and active research out there about how you can simulate this wider world. And it's not a Ubisoft game, unfortunately. It is not RimWorld. This is a game called S.T.A.L.K.E.R, and I mentioned it earlier as part of our goal-oriented action planning because it just so happens to use that as well. But there's some very, very clever tech that this game uses, and it's about 13 years old now, I think, this game. It's very old, but it uses some really, really fascinating tech, which we're going to be talking about. So, yeah, with this kind of rough idea of emergent simulation, simulating stuff that we can't see, as well as what we can see, we need to bear in mind this idea of AI resolution. So, in a typical game with AI and NPCs, every single AI agent on the map is going to be a high resolution one, right? And what I mean by high resolution is it's fully simulated. You know, if you think of it like, I don't know, probably in bad taste for me to bring Cyberpunk up. I wrote this when before Cyberpunk came out. But if you think of an NPC that you might or might not see in Cyberpunk, you're seeing them in full simulation, walking around. You can interact with them, shoot them if you wanted. Um, the This is kind of the idea of traditional AI. And as soon as we're kind of out of the range where it's viable for us to render this guy, this NPC, whatever, or have any reasonable interaction with it, we just cull them. We get rid of them. They're gone. They're deleted, essentially. You know, delete key in Unity Inspector, whatever. They're gone. So this is our what we'd consider a high resolution AI agent. But when we look at the low resolution AI agents, this isn't something that's typically used outside of these like emergent systems, but a resolution AI, in the sense of emergent AI, is something that you can't necessarily see at this stage. They're being simulated in some degree in the background, but they're not something that you can directly interact with. They just exist in memory, if you imagine it like that. Then these low resolution agents can be up-resed up to a high resolution sim when the player, you know, gets close to them or something. So what we end up with this idea of then is having varying levels of AI complexity based on where you are in the world, almost like a LOD system. If you imagine like LOD, you know, level of detail in games where, you know, buildings start to turn to Play-Doh if you walk far enough away from them. Again, the cyberpunk potentially. This is kind of this idea that this emergent AI system is based on. Yes, zoom up. Ben Sunshine Hill called this a simulation bubble. Yeah, that's a very neat term. I've not heard that one before, but yeah, that's really good. I've heard it called simulation bubble now. I've never heard that one. I've heard it called like a relevancy sphere. That's kind of used for a lot of things in like Unreal Engine and things like that. But relevancy is one. Simulation radius, I suppose. But yeah, simulation bubble sounds nice. So I think I'm going to steal that one. I'm going to use that one. Zoompub, thank you. We'll consider it a simulation bubble from now on. So in Ocean Rift, fish are fully simulated if the players can see them. Yep, absolutely. Okay, but they always exist in memory. Nice. So I guess, Chris, with that, I guess if you were to then kind of go away from that fish and then come back a bit later on, it will get up-resed back to like a high resolution one that you can see, but it will maintain that sort of that status it gained from that time that it was being like a low resolution fish in memory. I'm guessing. I've not played the game, but that sounds like how a system like that would work, given this concept. So I mentioned we'd talk about S.T.A.L.K.E.R. Again, I apologize for the formatting. Something horrible's happened here. I don't know if I can. I don't know if I can fix this. Yeah. Okay. I apologise. I don't think I could fix this formatting, but I hope that you somewhat get the gist of what it's trying to say with that key. But yeah, when we look at AI, emergent AI, S.T.A.L.K.E.R was a game from 2007, which I wouldn't want to say pioneered, but it made it very, very mainstream, this idea of emergent simulation. I keep saying it, I'm sorry. This is getting to me as well. They called it A-Life. I can only imagine they called it A-Life because it was a play on artificial life, artificial intelligence. There's very, very little documentation on this, and the documentation that is around for it is from modders. So um, take that as what you will. But we get a rough idea of it, and you can see it in game, so it's pretty trustworthy. But essentially, the idea is we've got our simulation bubble here, as we're calling it now, which is in the area that our player's in, which is our little blue dot. Every single one of these little red dots is kind of blending in with my laser pointer look. Every single one of these red dots is a fully simulated AI that you can see, you can shoot, you can interact with, you can talk to. That's all fully simulated. But when you look at these other regions of the map, I should note as well with this game, it's got like little load zones. That's what this this is a screenshot from the game, so it's a little crusty. But you can see the blue arrows here are basically load zones into different areas. So these yellow boxes are, I guess, are offline simulation bubbles. It's where anything in this kind of area is low resolution, it's de-resed, and it's being simulated to some degree in the background. And I'll get on to what that means. I don't have another slide for this actually, so I'll get onto it now. That when they're like low resolution, when they're in low resolution mode or offline, they're considered in S.T.A.L.K.E.R. They're still being simulated to some degree, so they are technically in memory around that area of the map. And their kind of patrols and things are simulated. So say you had one bubble here, we'll say this yellow bubble is a squad of bandits, and in this yellow bubble it's a squad of radioactive zone dogs. They call them blind dogs in S.T.A.L.K.E.R. These are radioactive dogs in the exclusion zone. And you can simulate these, they simulate the paths and the paths they're moving on, right? And say they have a collision, they bump into each other, they'll start to fight in memory. And I can imagine it would be somewhat of like a Pokemon battle encounter, right? If you imagine it just being simulated in memory, they're fighting and it's constantly working out who's winning and the chances of like what side winning. But that was all low res. Say you come into it, you come into this load zone. So this yellow box here is now our high resolution zone. Everything that was low res in that area is now considered up resed. So we make them fully simulated. So the things that were just in memory, like fake fighting, I suppose, are now spawned in as actual entities, and they'll carry on kind of fighting as they would be. Or say you caught the tail end of the fight and it was all over. When you enter that area, you might find a ton of bodies or whatever. And the whole point of this system is to try and keep every area of this map seeming alive, even without the player, and to keep the zone moving forward in time, without input from the player. And normally in this game, in S.T.A.L.K.E.R, is very abstracted. You wouldn't really know about this stuff. It'll just happen quite emergently, which is really fascinating that they kind of hid that behind the scenes. But there are a few mods out there. If anyone plays this, I would recommend one mod, which is I think like the radio mod or something. And essentially, it'll add like a little thing in your HUD, kind of here. If you think of my screen as like the gameplay screen, right? That whenever something kind of interesting happens in this simulation, it'll give you like a little diegetic update, so like an in-game update. Say these bandits start getting attacked by dogs, they might send out a distress call, say, oh, we're being attacked by a pack of dogs in the Red Forest area of the map. You could then go there and be like, oh yeah, they were right. And you can go and see that, and you can see where this sort of system makes for a really exciting game, and just to keep things alive and keep things constantly moving. So it's really fascinating. I'm going to go through a few questions. I apologise, I've missed quite a few. So Zumba Pup, Ben wrote a paper about alibi generation. Generated a statistical model for a plausible backstory of characters, went from low res to high res. Right, so that's really interesting. We'll be getting onto that in a minute in another game, which also had this idea of like an alibi system. But yeah, this is a very, very similar concept, and it's all kind of comes down to this idea of like a life simulation. But yeah, it's very exciting. We'll actually be getting onto that in a minute. I'm going to move the slide on to here. Again, I don't know what's up with the formatting. I apologise. It looked very pretty when I saved this in PowerPoint last night and did finishing touches. I don't know what Google Slides has done to it. I can only apologise. Yes, A-Life is an active field of research, as Chris pointed out. This is something that's still very big now, and it's constantly being worked on and researched on. And another one from Zumba Pup. Alex C on Tomorrow did a great interview with S.T.A.L.K.E.R's AI's devs, by the way. Oh, okay. I've not seen that. There's very I've been trying to find some documentation for the system for a long time for A-Life, but I've never really been able to find anything concrete or substantial. So basically, all the sources I've got is from playing the game a lot and looking at modders documentation, basically, and looking at mods that try and expose these systems. So yeah, that'd be really exciting actually. I'd like to see that. So yeah, moving on to a more recent game that also used this sort of system. So this also uses this idea of alibi generation, which Zumapup mentioned a moment ago. Watch Dogs Legion has this idea of play anywhere. This was kind of their what would you call it? Like their mantra for the game, right? Watch Dogs Legion, play as anyone. That would be their advert if they still did TV adverts for things like this. They probably do. I don't have TV. But yeah, we're going to go on to how their system works, and we're going to see a lot of parallels with this to S.T.A.L.K.E.R. So again, we have this idea of a simulation bubble around us and our player's position. So any NPCs that are kind of spawned in this area that you then interact with, so you maybe bump into, or you, if we go back a slide, you bring up the little kind of the profiler on them, I suppose. I haven't played this game, so I would imagine that's the sort of lingo they'd use. When you like hack their phone or whatever to get all their info, and you can see it's generated them a name and a look and a job. And there's been a ton of quirks with that system, as you're probably aware. There's a lot of memes and jokes about it around on the internet. But anyway, if anything like that happens, if there's any kind of interaction, that NPC is considered up-resed permanently. That's an AI, that's a character that's now stored in the game in some kind of database, offline database. So any NPCs then that are associated with that NPC, say, family, friends, associates, they're also up-resed, because, you might get this AI when you hack them saying, oh, I don't know, walking to the park to play a game of chess with father or something. I don't know. That other character, that father, is then an actual character in the game world. Whether they're low res or high res, if they were low res, they'd be up resed, right, to match the status of their kin. So it just means that you can then go and interact with them. But then again, if an AI leaves this relevancy, say it leaves a simulation bubble, and we haven't interacted with them at all, so we haven't got their name, we don't really know what they look like or anything, we have no reason to we don't need them, basically. So they're just, they're deleted, they're gone. We don't need to keep them in simulation at all. So they're considered low res, but they're also deleted. Their character never needed to be like fully fleshed out or generated by this alibi system. So just like in S.T.A.L.K.E.R, the down-resed AI, the AI is immediately down-resed when they're not in kind of relevancy or in this simulation bubble. So just like this alibi system we mentioned a minute ago, Watch Dogs has this idea of Watch Dogs Legion has this idea of a deep profiler. Which when you interact with an NPC, you scan them, or I think you recruit them. I think that's the word I'm looking for, actually. I've not played the game, so if anyone can vouch for that, or if anyone can correct me, please do. For anyone who has played the game or knows more about it than I do. You can recruit them, right? That's the idea of the game, I think. You can then deep profile them, right? And then the idea of the deep profiler is... no worries, but thank you for coming along. I really appreciate it. Thank you for the contributions as well. So this idea of the deep profiler, you can then break down all the day-to-day tasks of these AI. I'm going to race through this because I haven't got much time. I've just seen the time. Apologize. But yeah, you can start to see where these really complex kind of behaviors start to come from, and you can follow these AIs around and actually see them do this, provided that they're up-resed. When they're in kind of low resolution simulation mode, they work just like our S.T.A.L.K.E.R bad guys or other AIs that are outside of our simulation bubble. They'll technically be doing these actions in the background, in memory and simulation, but they won't be doing it to like a degree where you can go and see them, or they're being rendered in.
But, I will. Just jump in to say, if you want to run over for a bit, don't worry too much about the time, because the recording will be there, as of all the enhancement tweak stuff after the fact, so you take your time.
Okay, no worries, brilliant. Okay. Well, no need to hurry then. But that's basically, I didn't want to spend too long on this because I don't really know enough about this game and how it works, and it's much newer. So obviously there's not quite so much documentation on it. But the main point of all that was really just to show you where stuff is going and how we're kind of digging up these older systems and things from the past, and we're still using them today. And I hope you can kind of see where a lot of this stuff can be used now. I hope that maybe some cogs have been turning and you've been thinking of little like ideas for games and things where you can use these systems, because they by no means have to be very complex at all. You know, obviously Watch Dogs is an insane way of implementing it, but Ubisoft, the AAA studio, you know, it's generally these experimental smaller games where you add a goal-oriented action planning system or an alibi system. These are the games that really tend to push industry forward in terms of what's considered the new technology and the cool hip thing. You can remember a long time ago when a game called Facade was a thing. I don't know if anyone's played that, but that was considered a very complex AI based game, and obviously you wouldn't get a AAA game based on that kind of tech. It was pretty primitive, but it was exciting and it was new, and it was these experimental games that really helped push the industry like that forward. So I really see a future where like all of this can be moved, pushed together somehow into this big kind of sprawling, AI-driven game, basically. Or much smaller experimental games, because they're great too. We love to see that, and like I said, they're the ones that tend to push our standards forwards in terms of what we're creating. But without spending too much longer on the future of AI, I sort of wanted to leave you with this. Obviously, it's a bit tongue-in-cheek, but don't have good ideas if you aren't willing to be responsible for them. I by no means believe this has to be the case. It's a bit tongue-in-cheek, as I say. But if anything at all here has sparked any kind of remote interest in the subject area whatsoever, go ahead and do it. I've tried to make this as accessible as I can to show you really how accessible it is. A lot of this stuff, behavior trees, and as was mentioned in the chat earlier, Unreal has a HTN, or a hierarchical task planning network or something. I can't remember exactly what it stood for, but it's essentially goal-oriented action planning, and of course has a suite of behavior tree tech as well. So all of that's super accessible, and by no means does it have to be complex. It's quite threateningly simple to make something seem intelligent, and you can have a lot of fun in the meantime, making things act intelligent and make fun games that predict what you do and react somewhat credibly to the things you're doing. But it's a really fascinating area, so I really hope that this has resonated with some of you, or it's sparked something and you're going to be the next big AI in games innovators. I'm sure. Just remember to cite me if you do. Joking, obviously.
There's been a question in the chat. Will there be more episodes of this topic?
Right.
Tempted to go into full-time AI streaming, Will?
I'd love to, honestly. I have no idea where I'd start with something like that. Obviously, everyone kind of romanticizes the idea of maybe one day being able to quit a full-time job or whatever and be like a streamer or something, but I don't know. We'll see. I don't think I've got enough to say for myself really for that. I think I'd run out of things quite quickly. But I'm glad the interest's there. I'll bear that in mind. I'll consider that as something else I can do. But no worries, Harry. Thank you for coming along. No, I really appreciate it. But yeah, if there's any questions as well, anything that you want to talk about with, in regards to the game industry, placements, AI or anything, or just fancy to chat, I've got a link tree there with contact stuff. So there's email, there's Twitter, there's LinkedIn, and all sorts there. Oh, fantastic. Thank you, Tom. I appreciate it. With that being said, that's me done, I think. So thank you all very much for coming. I hope this has been a lot of fun. I've had a lot of fun. But yes, hope this was valuable.
Brilliant. Thanks, Will.
Great.
And everyone for tuning in.